Thank the organizers for this amazing week, and I wish you the best for this upcoming 6 months. You can hear me, right? Okay, perfect. So, as you can see, my talk is about Port-Hamiltonian systems. I am specifically interested in developing and analyzing numerical linear techniques for Port-Hamiltonian systems. And today I will start with what is their underlying structure, and what they look like, and what are some nice properties, and how we can solve them. And okay, first of all, why Port-Hamiltonian systems before what Port-Hamiltonian systems? Port-Hamiltonian systems combine the classical Hamiltonian approach with the network approach. It also extends the classical systems with including of dissipation and interaction with environment. So if you are interested in control problems, it becomes quite useful. It also uses energy as a language between different systems, so you can treat multi-physics systems easily with the Port-Hamiltonian framework. And the other nice thing is that if you are looking from numerical points of view, you can use Galerkian projection or model order reduction. You can still have a Port-Hamiltonian system, and they are passive. So I hope it convinces this is actually a good idea to use. Like they are passive. I will come back to that later, but isn't that they satisfy the time derivative of the storage function will be less than the input energy we are giving to the system. So some of these nice properties actually coming from their underlying Dirac structure. So we will have a space of flows denoted with F, and in a physical example you can think this is a velocities or currents. And then we will have E, which is the dual space of F and called space of efforts. And in a similar setting we can think them as a forces and voltages, if these flows and efforts may sound confusing in the first time. And so this is the associated inner product on them, and inner product of E and F will give us the power associated to that port. So Dirac structure is, well, here the constant Dirac structure is a linear subspace of F cross F, E, such that dimension of D is equal to the dimension of F, and their inner product is always 0 for every element in the Dirac structure D. So this actually helps us for the power preserving in the Port-Hamiltonian systems. And the nice thing about Dirac structure is that if we connect them in a smart way, and then we get another Dirac structure, the way to do that is we need to have a common space of shared variables called shared flows and efforts, and we assign the flow of one as a negative of a flow. So if it's like in going to 1, it should be out going to 1. And in this way, when we have their inner dual product, then they will be cancelling each other out, and then our system will be energy preserving. So this is a figured alpha out. So it's the same space, but just in a minus sign. Also, other way to do it is that you can also assign the efforts in a minus sign. It still works.
Sorry, are these systems ordinary differential equations, or
they could be or ODEs or differential algebraic equations.
They could be DAs.
Yeah.
Are they control systems? So there are.
They could be control systems. Yeah, they are quite useful in that sense. Yeah. So we can also have input and output, which will be corresponding to our external ports. I'll get back. And if we just compose the Dirac structure in a smart way, in a power preserving way, and then we have this theorem, which I will not prove today, that this composition of Dirac structure is again a Dirac structure. So we can build Port-Hamiltonian system connecting their Dirac structure and have more complex systems from like a simpler blocks, like a Lego. Yes, please.
What do you mean when you say power and power preserving?
I mean is that Hamiltonian gives us the energy of the system or the power. I use power and energy usually interchangeably.
So power means the same as energy?
Yeah, for my point of view, yes. And what I mean is the power is the inner dual product defined on the flow and effort spaces. Proof of this theorem and more details on Dirac structures can be found in Arjen van der Schaaf's 2014 Port-Hamiltonian book. Yeah. So what are these elements of this system? So we have energy storing elements, and we will denote them with Fs and Es. And we will connect them to our system with this assignment. The next elements are energy dissipation. So this is the extension of Port-Hamiltonians, and this is how they define. So this should be less than or equal to, so that they are energy dissipating elements. And the next one is external ports. So this will be our actually input U and output Y. That's why how we can also control the systems. And when we are connecting to system, one way to do it also, trade input of one system for output for the other, output of the other system, input for the other system. And also we have energy routing elements, which can be considered as one Dirac structure, since the composition of Dirac structure is again a Dirac structure. So Port-Hamiltonian system in a nutshell looks like this. So we have storage elements, ES and Fs connects to the Dirac structure, dissipation, ER and FR connects to, and so open-ended, so it can interact with the environment or other systems. If you would like to write a power balance equation, and the change in the Hamiltonian will be R minus the power in the storage, well, the change in the power. And this will be equal to the ER transpose FR plus EP transpose FP. Since they were in the elements of the Dirac structure, this should be 0 by definition. And since this should be less than or equal to 0 as the dissipative elements, we got this inequality. Thanks. So Port-Hamiltonian system altogether consists of energy storage port S, resistive structure R, an external port P, and the total Dirac structure D. And the dynamics of the system is imposed by the definition of the Dirac structure. And if you would like to put all together, Dirac structures can be considered as graphs of skew-symmetric matrices, as skew-symmetric functions. And if we, And if we say that we have a linear dissipation relation, then we can write the ER as minus R bar FR, where R should be a positive semi-definite symmetric matrix. And when we put them all together and plug in what is Fs and Es was, then we get this system. So it can remind you of the Hamiltonian system, just we have the dissipation here and we have also input and output. And this is generally how they look like. So I'm here focusing on the linear Port-Hamiltonian system just for the simplicity and convenience. And this matrix E can be a mass matrix, can be identity matrix corresponding to the differential equations, and a 0 block for algebraic equations. So it could be singular, but it's a symmetric matrix. So yes, J is the structure matrix coming from the Dirac structure, R is the dissipation matrix, and these are for the external ports, and F is the feed through.
Is E invertible?
No, it could be singular. Yeah. So most common example of E is the identity block and then 0 block for the algebraic equation. So it doesn't have to be invertible. It would make our life easier if it was though. So I say that we can build them like Lego. So how do we do them? The way to do it, we have the Cartesian product of the spaces, state spaces, and we just add up the Hamiltonians. So this energy of the system is the summation of the energy of subsystems. And the Dirac structure is the composition of the previous Dirac structures. So passivity, from control point of view, this is the passivity definition we use, but I don't know if there are other passivities. So let's say we have this system and we have a differentiable non-negative storage function s from x to r. If it satisfies this passivity inequality for all solutions of x correspond to input u, then we say that a system is passive. So if you remember the power balance equation from the Port-Hamiltonian systems, we had that time derivative of Hamiltonian is less than or equal to our power coming from input and output, external port. So if we assume that Hamiltonian is bounded below, which we usually think that's a natural assumption, that energy wouldn't go to the minus infinity, then our, any Port-Hamiltonian system is passive with respect to the external port variables and the storage function Hamiltonian. And another nice thing is that we can transform these Hamiltonian systems and again get another Port-Hamiltonian system with the same Hamiltonian. Change of basis or scaling our system doesn't affect the amount of energy in the system. It's still a fixed amount. So what do we do is just, if we have pointwise invertible u and v, we can transform our systems to this one, and it will be still a Port-Hamiltonian system. But this usually comes useful when you have a Galerkin projection or you want to do model order reduction. So this was I wanted to briefly mention about what is their underlying structure, what they look like. But what I'm mostly interested in is the part, how can we solve them? So our idea was that, okay, for many applications we are dealing, we need to solve a discrete system of Port-Hamiltonian system. Let's say it looks like this. It doesn't have to be necessarily the same EJ-R matrices, but they have the same structure. And we decided that it would be a good idea if we group the symmetric parts, use as a preconditioner, and try to derive a short recurrences like Lanczos for symmetric matrices. So if we have any linear algebraic system A equals B, we can always write A as a symmetric part minus a Q-symmetric part. And here our assumption is that M is positive definite. So if we multiply with M inverse, we get this equivalent system. I minus kx equals to B hat, where k is M inverse n, and B hat is M inverse B. Our method actually quite depends on this operator k. So a matrix is called B normal S if the B adjoint of A, which is this B inverse A transpose B, can be written as a polynomial of degree S, but not smaller than S. And then we can say that, okay, A is normal of degree S with respect to B. And if you look at our K operator, M adjoint of K, M inverse K transpose M is minus K, so it's a polynomial of degree 1. And then we get that K is M normal 1. And this theorem tells us that the matrix A admits an optimal S plus 2 term recurrences if and only if A is B normal S. So our K was M normal 1, so it admits a 3 term recurrences relationship where these coefficients alpha j, gamma j, and beta j is chosen so that the vectors Vj's would be M orthogonal. And here we assume that initial vector was M inverse F. Okay, it should be B, M inverse B. So Widlund used this Lanczos relation above and projection property such that when we are looking for xj in the J-Krylov subspace generated by K and B hat, residual B minus AXJ should be orthogonal to the J-Krylov subspace. And in the same year, his PhD student Rapoport implemented the same Lanczos relation with a slightly different projection process, where the residual should be orthogonal to I minus K J-Krylov subspace. And this reminds us of GMS for left preconditioned systems. And if you would like to write the GMS in a similar way, we get this. But here the differences comes from, we have preconditioned residual should be orthogonal to the same space as in the Rappaports. But all these three methods, is there a question? Okay. All these three methods are always looking for xj in the J-Krylov subspace, but they have different minimization properties, they have different projection properties. So we thought, which one is better? Is the next question came to our mind. So we tried them with an example. Actually, we also took the example from Widlund's paper. And here we are also comparing them not with the original method, but with the fully orthogonalized version, since Lanczos vectors in finite precision used to tend to use their orthogonality quite quickly, and I will also show that in a second. So let's say we have these partial differential equations, and it was carried out with a difference approximation, and here we took the step size h 10 to the minus 2. Our matrices are 2500 by 2500, and the tolerance is 10 to the minus 12. And the stopping criteria is that preconditions relative residual should be less than tolerance. So if you look at the examples, we take the A constant for parameterizing, easier way. And we see that for a relatively well-conditioned problem, they behave in a quite similar way. But when we increase A and we have a worse conditioned problem, we start to see that Widlund, Rappaport, and GMS is this black one, start to differ from each other. And we were curious what is that reason could be. And then we check their orthogonality. And we see that the orthogonality, even for the well-conditioned problem, Lanczos vectors start to lose it very quickly. So, and if we came to the A equals 1000, we see that after the step around 30, they almost lost all of the orthogonality between the Lanczos vectors. And this is causing us delays in the convergence, stagnation. And when we look at the orthogonality of the fully orthogonalized system, we see that, okay, we can keep it in the level machine 0, but it takes us more time to do fully orthogonalization comparing to their original versions. But still, they are faster than GMS, even though they are taking same number of steps or more steps in the original case. They are still faster than GMS. So we are thinking that this is a quite promising approach, and we should make use of a short-term recurrences. But we shouldn't lose the short-term recurrences by using a fully orthogonalization method. So currently we are working on more efficient reorthogonalization techniques, similar to the partial orthogonalization or selective orthogonalization for symmetric Lanczos. We also would like to extend this to the case where M is not positive definite, but positive semi-definite, because in our case for Port-Hamiltonians, E could be singular, R could be positive semi-definite, so it's not for all cases yet. And the other thing we would like to do is that use this idea to solve Port-Hamiltonian eigenvalue problems as well. And here are my references. If you are interested in Port-Hamiltonians, Arjan van der Schaft has quite a literature on this. And I would like to thank you for your attention.
Thank you very much for your talk. Now we have time for a few questions. Are there any questions?
There's one thing I never understood about Port-Hamiltonian system. It's that dissipation is formulated as this inequality between efforts and flows.
Yes.
But in the end, you get a system where there's no inequality anymore. So just equality. So.
Okay, let me get back to, okay, here's. So we have, as in the sense that the change in our system, the change of energy in the Hamiltonian should be that how much we lose it to the dissipation and how much we gain from the input. So that's why it is less than or equal to this one. So we have that inequality still preserved here, if that answered your question.
Why don't you solve a constraint problem? Why can't you solve just a normal problem and not without constraint?
I didn't understand that.
Maybe I ask after.
Okay.
Yeah, I was wondering if it could be possible to use a BCG stub type of approach. If that, if you have been thinking about that.
Yeah, so we think about like biconjugate gradient and also the Golub and Konkus method of Hermitian and skew-Hermitian splittings. And this method was actually faster than all of it, so we chose that to continue on this path. So our first ideas was actually the Hermitian skew-Hermitian splitting from the Golub, and the second idea was using BiCG.
More questions, comments? If not, I think you will have quite a few discussions in the
Yes.
break. Thank you to the speaker again.
Thank you.